The two previous sections discussed the equivalency of non-parallel crystallographic directions and planes, where we have family of directions and family of planes. So here we see this is the 100 family direction. Assuming this is a simple cube, so along the 100 direction, which are the edges of this cube, we know that the atoms are in touch. So directional equivalency is related to linear density in the sense that for a particular material, again, if this is simple cubic, equivalent directions have identical linear densities. So all the edges, all the directions from this 100 family have the same linear density. So we're going to learn linear density just in a little bit. The corresponding parameter for crystallographic planes is planar density versus for direction we have linear density. So for planes we have planar density. So planes have the same planar density are also equivalent. So we're going to define planar density in a little bit as well. So just a quick kind of overview. The equivalency of planes means the family of planes. For example, the 100 plane family in a FCC structure. So here you see those are all the 100 or all the planes from the 100 family within the same unit cell. So all of them have the same planar density. The atomic arrangement on all of the planes are the same or are identical. The linear density is defined as the number of atoms centered on the direction vector divided by the length of the direction vector. So we're going to just focus on linear density for cubic systems, where we have the cube has the lattice parameter A. So all three sides or all the sizes will be, the length will be A. There's no A, B, C. Okay, so let's take a look at one example to see how do we find the linear density of aluminum in 110 direction. So first of all, we have to identify, well, to find the atomic arrangement, we have to figure out what is the crystal structure. So for aluminum, it has FCC structure. So now you can see this hard sphere model of the FCC structure, and the given information is the lattice parameter A is given. We're looking for the linear density of 110 direction. So the 110 direction is the phase diagonal. So if we choose this corner as the origin, and we have the x-axis here and y-axis in this direction, and the z-axis in other direction. Now we have along the x direction is 1 unit length. Along the y direction, 1 unit length, we arrive at the head of the vector. So this is the 110, again, is the phase diagonal. Okay, so based on the definition, we need to find the number of atoms centered on this direction vector. So we can see there are 2 half atoms on both ends, and there's 1 full atom in the middle. So a total of 2 atoms centered on the vector. And next is the length of the direction vector. So the length, since we already know A is 0.405 nanometer, we can find the length of the phase diagonal, which is square root of 2a, because that is the 90-degree angle. So now we can substitute the numbers into this formula. The linear density equals to number of atoms centered on the direction vector, which is 2, over the length of the direction vector, which is square root of a. and substitute the numbers in. The answer is 3.5 inverse nanometer. So the unit of linear density is the reciprocal length, or length on the inverse length. The planar density is defined in a similar manner. The planar density equals to number of atoms centered on a plane divided by the area of the plane. So let's take a look at one example. We're looking for the planar density of 100 plane of BCC iron, and we're given with the radius of the iron. So first of all, let's take a look at the 100 plane of the BCC iron, or typically a BCC structure. So on the left, the hard sphere model, we have more than one unit cells. We have all the atoms stacking together, and here this cubic representing one unit cell. So for the BCC structure, we have one atom sit on each corner, and there's one in the body center. And the 100 plane is the front surface, or typically all the surfaces are one of the 100 families. So let's choose this front surface as the 100 plane and check the atomic arrangement on that plane. So we know the atoms are in touch along the body diagonal. So if we bring out the entire front surface of the whole arrays of atoms, and this is the front surface of that single unit cell. We have 4 atoms on the corner, and again, those atoms are not in touch. Atoms are in touch along the body diagonal in another direction. So here is what we see for this 2D repeat unit, the 100 plane. And to find the planar density of this plane based on the formula, we need to get the number of atoms, and we also need to get the area of the plane. So first, let's take a look at the atoms, number of atoms centered on the plane. So those are the atoms centered on the plane. Okay, we're only counting the atoms within this plane, not like the atoms outside the plane. So now you can see there are 4 quarter atoms. So add them together, we have one whole atom centered on the plane. So the top part is 1. We have 1 atom in total centered on this 100 plane. And next, we need to get the area of the plane. So it's a cube. It's a cubic, or it's a square for this. It's a square for the 100 plane. Sorry, it's not a cube, but it's a square. And the side, the length of the square is A, the lattice parameter, A. But we're not given with A directly. We know R, the radius of the iron. So from there, we need to get to R, or to A. So we need to find a relation between A and R. So that's a very important relation we need to know. For BCC structure, since the atoms are in touch along the body diagonal, let's just do a quick review. So the body diagonal looks like this. This is the body diagonal. And A on one side, and this is the square root of 2A. And the atoms are in touch along this body diagonal. So here's one atom in the center, and half here, half there. So if I'm going to bring it out in the 2D plane, so this is the side A on the top, square root of 2A, and the atoms are lying over here. Not very good drawing, but just like that. Okay, so now we have 4 R's. So this is 1 R, 2 R, another R. 4R equals to square root of 3A. So this is the relation between the radius of the atom and the lattice parameter A. Okay, so from there we can solve A in terms of R. So it's 4 over square root of 3R. So that's this relation. And R is known. We substitute in the value, then we get the lattice parameter for BCC iron. And area of the plane will be A squared. So let's continue with the calculation. A is calculated to be 0.287 nanometer, and number of atoms centered on the plane is 1. Therefore, the planar density PD equals to number of atoms centered on the plane over the area of the plane, A squared, which is 1 atom over 0.287 nanometer squared, and the answer is 12.1 atoms per square nanometer. So keep in mind the area is not always A squared. This is only, A squared is only for the 100 plane, is the surface or is the one of the surface of the cube. But if you're looking for the 111 plane, for example, or 110 plane, the area will be a different value. You may remember from some calculation you did earlier on the metallic crystal structures that both the face-center cubic FCC and the hexagonal closed packed crystal structure HCP have atomic packing factors of 0.74, which is the most efficient packing of equal-sized spheres or atoms. In addition to unit cell representations, these two crystal structures may be described in terms of close packed planes of atoms. So let's take a look at what is close packed planes and directions. So we'll start from 1D. Close packed structure in 1D. So think about you have a lot of balls, okay, and you want to put them in a row. So the most efficient way to place the balls in a row in 1D is like this. So each atom or each ball is in touch with its adjacent atoms or adjacent neighbors. There's no gap between the atoms. So this is the closed packed structure in 1D. And now let's add another row so to make it a 2D packing. So there will be two ways to add a second row. One way is to add another row directly below the first row, and the third row directly below the second row. So in this arrangement, each sphere is in touch with 4 other spheres, leaving a diamond-shaped void. And the second way to pack it is to shift the second row so that each sphere is on the depression of the first row. And in such packing, the spheres of the third row are aligned with the first row. So in this arrangement, each sphere is in touch with 6 other spheres, and these 6 spheres formed this hexagon. And so that's why this arrangement is called hexagonal close packed arrangement. Again, compare those two packing methods. The left one is not close packed, we have bigger Ys. We can pack it more efficiently by using the second method. And this is the most efficient way we can pack all the atoms or all the balls, spheres in 2D. And this is the closed packed in 2D. Now let's move up to closed packed structure in 3D. A 3D structure can be generated by placing 2D layers on top of each other. And there are two ways to do that. The first method is to place the second layer in such a way that the spheres of the second layer come exactly on top of the first layer, and the third layer exact on top of the second layer, and so far so on. And this is an inefficient way of filling the space, and the result will be a simple cubic lattice. The second way to stack a second layer on top of the first layer is to place the second layer on top of the depressions of the first layer. And now we can see there are two types of depressions, or two types of voids, a type of B voids and C voids. So for the B voids, you can see it's triangular voids with apex pointing upwards. And C voids are triangular voids with apex pointing downwards. So now the second layer has to be either on top of B or on top of C only. We cannot use both because of the size of the spheres are the same. If we put on top of B, then there's no way to put on top of C for the second layer. So now for these two layers, A, B stack now so far is the closed packed layers, because that's the most efficient way to stack a second layer on top of the first. Here comes to the next layer. So we just talked about the first two layers. The first layer is A, and second layer is B, which is placed on top of the depression of the first layer. And the third layer can be again placed directly on top of the first layer. So we call that A layer, A again, A plane again. And so if we keep doing this stacking, A, B, A, B, A, B sequence, we will form the HCP structure, which is the closed packed structure, hexagonal closed packed structure. Again, the hexagonal closed packed structure is achieved by stacking A, B, A, B, and A, B sequence of atoms. So here is another look of this hexagonal closed packed structure, or HCP crystal structure. This is the A plane, or layer A, and layer B is on top of the depression of the first layer, and then A layer again. And we choose this as one unit cell. For the third layer, we have another way to stack it. Instead of doing A, B, we can actually stack the third layer on top of the C voids. So, look like this. First layer, A layer, and we have two types of voids, B voids and C voids. Second layer, we're going to put the atoms on top of the B voids. And next layer, instead of put directly on top of A, we're going to put on top of C. And this will result in the FCC crystal structure. So FCC crystal structure has the ABC stacking sequence. And this is the FCC unit cell. So to get to the FCC unit cell, we actually need to kind of rotate or tilt this ABC packing a little bit. So the closed packed plane is this 111 plane. So this is the 111 plane actually. If I can find a 111 plane with the right color here. So I should add one more atom here. Again, it's not look good, but that's the atoms on the 111 plane. You have to tilt it a little bit to match this unit cell you see over here. So this is the 3D view of the ABC stacking sequence for FCC structure. Again, if we put the layers horizontally, this is the A layer, B layer, C layer, ABC, ABC. But when we choose the unit cells, this A is not the bottom surface, is not 100. Instead, this close packed layer is the 111. So this is the A layer. We have to tilt it in this representing the 111 plane within one unit cell. Okay, versus this is the horizontal plane. We have to tilt the packing, the stacking, and to choose unit cell. So within the FCC structure, the closed packed direction is the 110 direction, so which is the face diagonal. So this is the 110, another face diagonal 110, and 110, the front face. So my drawing is not quite straight, but I'm drawing the 3 face diagonals. And there are more diagonals, of course. All of the face diagonals are closed packed directions. And the closed packed plane is the 111 plane. So is the plane passed through the face diagonal or enclosed by this 3 face diagonal. So that's the 111 plane. Let's summarize the closed packed directions and planes in different crystal structures. First of all, in the simple cubic structure, SC structure, the closed packed direction is the 100 direction. So that is the edge of the simple cubic. Or the edges, all of the edges belong to the 100 family. So along that direction, the atoms are in touch. So that's the closed packed direction. And there is no closed packed planes, because for a plane to be close packed, the second row should be placed in the depression of the first row, but for simple cube is not. So again, this is the close packed plane, but for simple cube we don't have a plane look like this. So for BCC structure, for the body-centered cubic, the close packed direction is along the body diagonal, 111 direction. So there are 3 atoms along the 111 direction. So I'm just going to do a quick sketch. This is the body diagonal. So the atoms are in touch along this 111 direction. One atom at the center of the body and 2 corner atoms. So this is the 111 direction. There is also no closed packed planes in the BCC structure, because we cannot find a plane satisfies a packing like that. For FCC structure, we have the closed packed direction is the 110 direction, which is the direction along the face diagonal. Just gonna draw one face diagonal. Along this face diagonal, we have one atom at the center of the face and 2 atoms at each corner. So that's the 110 direction. And the close packed plane is the 111 plane, which is the plane passed through the body of the face-centered cube. So on this 111 plane, the packing of atoms are looking like this. So this is the most efficient way to put all of the atoms together. For HCP structure, it's also a close packed structure. So this is just for your information. You don't have to know the direction and the plane for HCP. So all of the edges of the HCP cube is close packed direction, and the planes are the top and the bottom plane. So materials with FCC structure including aluminum, copper, gold, silver, and other materials. And usually they are ductile. So materials with BCC structures including sodium, potassium, chromium, and the material with BCC structures are hard and less ductile, which means they usually are brittle, easy to shatter. So, why should we care about what plane and what direction is close packed and what is not? Does it really matter? Well, in general, properties depend on the linear and planar density, or the linear and planar density will affect the property. For example, later we will learn the mechanism of deformation in metals, which is called slip. So this slip depends on linear and planar density. It occurs on planes that have the greatest density of atoms in direction with highest density. Or this slip or deformation usually occurs along the close packed direction on the close packed plane.